So welcome back, everyone, to this meeting today. A very important meeting about the material science and the importance of materials for our society. So this session 2. I have the honor to share this. My name is Lars Montelius. I'm the Director General for INL, the International Iberian Nanotechnology Laboratory, headquartered here in Portugal, in Braga. I'm also professor at Lund University. So now we have a very intense program, and this session is called Advanced Materials as Accelerators of the Digital Economy. And it would span things from machine learning, AI, to flexible electronics, embedded electronics, and to different kind of composites, etc. So it's very interesting. And without further ado, I would like to introduce the first speaker, which is Gianmarco Ignanes. I'm sorry if I don't pronounce your name correctly. You can change later. So, and this is a talk entitled "Machine Learning in Material Science and Engineering." So the floor is yours, please.
Thank you very much for the introduction. And I first would like to thank the organizers for inviting me. So can you see my screen correctly? Perfect. Okay.
Yes.
So indeed, you know, when we think about big data and machine learning, these are revolutionizing material science. Indeed, you know, in the past, we used to rely mainly and essentially on experiment. Then there was a move to developing theoretical science that could start making predictions. Then we started using those laws that were derived from the observation of experiments to make computer simulation and also predict behavior of materials, for instance. And then most recently, there's been the fact that, thanks to the fact that computers are going very fast, the experiments are being made faster, there's amounts of data that are available, and it starts being possible to use artificial intelligence to use these data and then analyze them and then also make predictions. So if we look at the amount of papers that are being published, so this is a search for material science and machine learning in Scopus, as you will see here, basically the, sorry for this. Okay, so the amount of papers that have been published has increased drastically in the last few years. So this is the reason why I kind of changed my title, in a sense that I can only present you a very personal and biased view on these efforts. If you look at the countries that are publishing, there's no surprise that the United States are quite ahead, and I will say why it's no surprise. China is doing a lot of work, but Europe is not doing too bad either. So the reason why the US are doing very well is that you have those companies like Facebook and Google that are also doing research in material science. It's quite interesting to see that they are devoting the power that they have to doing things like catalyst and then learning things on other materials subjects, biomedical and chemistry and so on. So it's no real surprise that because of their, what they have developed in terms of AI already can help in doing machine learning as well. So as I said, Europe is not doing too bad, but I think that we could do better. And I would like to stress here initiatives such as the centers of excellence like MAX and NOMAD that are involved in gathering data. And I will say a word about these data and about developing machine learning tools. So in terms of the kind of articles, you will see that there's many articles, which is nice also is to have a number of reviews, which is interesting to then start entering the field of machine learning in this way by reading some reviews. There's a lot of them, so it's interesting. So just to show some of them here. And then the other thing that I would like to show is the distribution in terms of topic. And you see that material science and engineering is taking a big part of what's done in the broad range there that was investigating there. So as I said, data is really key to being able to get to do machine learning, and there's the number of databases that have become available online. And most recently, we have developed an API that is such that you can query the data that are available in those databases in the same way. The API is called Optimate, and you can really query all those databases. So this makes it makes it possible to find, access, and interpret these different databases and to reuse the data. That's the FAIR principle of data science. So this is all about data. Now, what can we do in terms of machine learning? So we know that in terms of materials, one important thing is the process of the materials, because the process of the material influences their structure influences their properties, and the properties influence the performance of the material. So we'd like to optimize this whole thing. So typically in the past, we've been looking in this way. So the deriving science relationship of cause and effect. So what should I do to my process to find such a structure? How should I change my structure to get such properties? And how do these properties influence the performance? So machine learning can help in devising relationship in this direction. So typically one could get a property as a function of the processing condition, the composition, and the structure. But most interesting is to go the other way around. So if I want to achieve a given performance, which processing should I use to get a given structure and to get the properties that I want? So this is called the inverse design. So this allows to maximize a property such that we have the best performance. So I'm just going to show you some examples of first this relationship, and then I'll show you some examples about the other one. So machine learning has been used quite a lot for optimizing the process parameters. In this case, that's an example where conductive alloys have been developed based on data that were discarded from previous experiments. And thanks to the fact that they were put in some databases, it was possible to then machine learn them and then make predictions of new interesting materials. Same is true here with fatigue, where again, some data-driven effort was made to predict interesting materials in terms of properties of fatigue using additive manufacturing. Maybe one important point is that in order to develop such relations, so going from the left to the right, it's important to be able to validate the new models that are being developed. And I would say a word about that because the way in which we work in material science is slightly different from the big data that is available for Google or even for images. And so it's important to develop benchmarks of the different models that are being proposed. And so this is an effort that is called MatBench, and where different kind of properties for which data sets have been gathered are being tested by using different models for the machine learning. And then you can see, if you go on the website of MatBench, you can see which are the methods that are most interesting for the thing that you are doing. So as I was mentioning, our field is a bit special because in most of the cases, we don't really have big data. The amount of data that we have is quite limited because it takes time to characterize many different materials. It takes time to simulate many different materials depending on the properties that you're trying to simulate. And so we've been recently developing a method that takes advantage of the knowledge of the physics in such a way that you can work with limited data sets, though achieving a very good accuracy. So you see here, we are predicting different thermodynamic properties. So the solid lines are the results that have been computed from first principles, and the dashed lines are the result of a machine learning. And you see that we can reach a very good agreement at a much lower cost. And this is really interesting. Now, I would like to go in the other direction of being able to target performance and create the specific process structures and properties such that that performance is met. So there are different things that can be done from that side. So this can be, so machine learning in this framework can be used to analyze experiments. So you can have automatic analysis of infrared spectroscopy, as in the example here. It can be X-ray absorption spectroscopy as in this one. And there is even these things where you probably know that in medicine, that's already the case, is can deep learning recognize microstructure as well as the trained human eyes? And we probably reach a moment where it's the other way around. So the machine learning would be better than the trained human eyes. So the last thing is to show you that there are already some examples going on about the machine learning inverse design. So this is an example in the case of molecules, but there is also some early efforts in terms of solid state materials or crystalline structures. So where basically you try to predict a structure that meets the requirements that we want to do. As I was mentioning, a lot of effort in machine learning has been devoted to images. And just to show you an example of what this inverse design is basically the fact that people are now able to generate the faces of people that basically do not exist. And so if we were able to do the same thing with materials, namely to kind of mix and say we would like the material to be more this and more this, maybe here you see we go from a young person to an older person, we could have something like that for materials, then we would be able to create the materials that we want with the properties that we want. And with this, I would like to thank you for your attention. Thank you very much.
Thank you very much. It was very interesting. So I encourage everyone that participates to put questions. You can use the chat if you like, and I can forward the questions. Some of you that are speakers, I think, can also speak maybe everyone can speak. I don't know really, but I would like to ask you some questions before giving the floor to the audience. So I liked a lot what you described here, and it made me to think a little bit about, I mean, first of all, the API, I mean, the Optimade, I think that is very important, right? To have a common API. So how can we get access to that? How do we, I mean, can we Google Optimade and then we get access to it?
Yes, so if you go to optimade.org, we have a consortium based on all these databases. There's a paper that's available on archive, and it's submitted for publication in Scientific Data.
Excellent, excellent. Then I have another question, which is, I think this inverse, let's call it inverse engineering, which is really inverse machine learning engineering, kind of, right?
Yeah.
And then you go from performance and then back to processing, so to say, right? But I mean, if you think this in a wider perspective, in the innovation perspective, could you do predictive or reverse engineering for, let's say, predicted innovations? I mean, a company has a certain, they would like to achieve something, and they say, this is what we would like to have. And then could machine learning to be used in order to go back the whole flow? I mean, selecting different materials, different processes, different.
So that's exactly what I was trying to aim at. I mean, for the moment, there's been a lot of work in this direction. So for the science relationship, because we know, for instance, the properties of a number of structures. But now that we have developed those models, you can go the other way around. And one way is like the phases that I was showing, to go the other way around, to say, okay, I would like to have, I don't know, a metal which has these properties. It can be a color, it can have a certain conductivity, and then if you have developed the good relationships here, you will be able to search the other way around and to make this inverse design. I mean, there are a few attempts to go in this direction already, but I think that's going to be the next coming paper.
But I think this is really interesting, right? Very inspiring. Okay, very good. Then just another question: what is the link between these? I mean, now the Material Genome Initiative that started maybe 10 years ago in the United States, right? What is the relation to the Material Genome Initiative and the progress being made inside that initiative?
There's a strong links, I would say, in the sense that, I mean, the Materials Genome Initiative resulted in the creation of these databases. And once you start adding, without databases, you cannot do machine learning. Now that we have the databases, models of machine learning have been created, and there's links with Optimade and the Materials Genome Initiative as well. So it's strongly connected to that.
Okay, very, very good. Okay, then let's see if there are any questions from the audience. So anyone would like to raise a question?
Okay. Can I raise a question, Lars?
Sure, sure.
Gian, one of the things that you present, and I think that should be the direction for the future, how we can design new materials with new functionalities, exploiting the properties, and using what I think is fantastic is the new tool for the future, which is the database.
Mm-hmm. So I didn't get the question. What is the question actually?
The question is how we can exploit machine learning to design the materials with new functionalities, like STEAM materials.
Yeah. So basically, I mean, once you have access to the databases, so basically you maybe create a subset of the database for the properties that you are targeting, then you can develop a model of machine learning that basically is able to predict the the properties that you are interested in based on the information that you have, be it the processing or the structure. So there are many available open tools out there. You go to GitHub and there's going to be plenty of models available. And from there you build this model, and then you have to, once you have the model, you basically can play with the processing parameters in such a way, and then the structure, the composition, in such a way that you achieve something that is close to the performance and the properties that you want. That's the way it is done, basically.
I mean, is it possible to include also, let's say, the raw material? I mean, the entrance point before processing. You also have raw materials. I mean, the material has a certain kind of composition, let's call it like that, right? I mean, could that be included? So you go all the way to make artificial compositions, so to say?
Yes, when I speak about structure, I mean, composition is included in the structure. So you have both the composition and structure, but anything for which we have a description can be used to machine learn afterwards. So that's the main point. So you have the data and you need to describe the data, and from there you can derive relationships.
But typically on this type of database, we just put the best database. And I think this will not help in identifying drawbacks. For instance, in medicine, you usually use bad data to understand the future.
Yeah.
In engineering and science, this is not too much the case. What do you think about this?
Well, I think it's important because you see here in this paper, you see here the machine learning models are trained from discarded experimental data that show undesired. So, if you keep all the data, even the wrong ones, there's a lot to learn there. So it's really important to keep all data, be it the good one, but also the bad one, because the learning is done both on the bad and the good thing. It's really important to do that.
Here, I think you touch on something that is very important, right? And that is, I mean, in science community usually only publish good data, right? And typically representative kind of good data, and they don't show or discuss so much about the failures, or let's call it the green fingers that you need in order to create or get this good data, right? But to have a more wealth of kind of descriptions of also things that failed would be an immense kind of portfolio of knowledge, right? That is kind of wasted today. That I think we should put more emphasis in the future. I think.
Yes, it's really important.
Yeah. Okay, I would like to say thank you very much for this very interesting.
Can I put a question?
Sure, Antonio.
Okay, so I have a question to you. So inverse design can in principle give an idea about the product or the compound that have certain properties. Okay, so I can see these quite easily, but can also give some hints about the processing, about how to prepare this compound, because sometimes you have that a certain compound with a certain composition, with a certain structure, could give that or those properties, but how to prepare it sometimes is not so easy. So these can also be obtained from here, or no?
Yes, provided that you have enough data that show you, if you try different processing condition, in what they resulted. Once you have information about how you go from here to here, so I don't know, changing the temperature, the pressure, the composition that we were saying before, the result that you get, once you have a lot of data like that, you can develop a machine learning model for that. And so you can go all the way from the processing to the performance. It's just a matter of collecting the data, even the bad ones, as we already said.
Okay, thank you.
Okay, thank you very much. So thanks again. And now we move to the next speaker. It's Sasuke Shimon from Nagoya University. And the title of the talk is Artificial Intelligence in the Materials Research. So please, Saskia, I hope I pronounced your name correct. Saskia, maybe. Please. We see your presentation, but we don't hear you.
Okay, now you should hear me.
Yes, now we hear you.
Okay,
very good.
the order matters. Okay. me see. Sorry. Okay, yeah, so first of all, I would like to welcome everybody to this talk and to thank the organizers for giving me this very nice opportunity. So today I would like to give an overview of artificial intelligence in the materials research. Of course, also in my case, it's also a somewhat personal perspective on this. The scope of this talk is a bit wider than the previous one, as it includes all kinds of artificial intelligence in the sense of everything that mimics human intelligence by some computational technique. However, many of my examples will still be from machine learning also, because the application of AI in materials research is still very much focused or centered in machine learning. So first, I would like to give some overview and examples of applications, then outline some challenges, and in the end, give an outlook on the other way around on materials for AI. So these are some subdisciplines of material science in which you can already find applications of AI in the broader sense. So characterization is probably the most advanced one, a prediction of properties, synthesis of materials, and less developed data extraction and theory discovery. So currently we have a significant gradient in the stage of development here. So first I would like to show an example for applications in characterization. Many of those applications focus on automated image analysis. And the example that I'm showing does video analysis of X-ray radiographic videos taken during the slow cooling of aluminum copper alloys. And the authors were able to automatically and efficiently analyze those data to detect the formation of crystals and to determine the formation rate, growth rate, and movement of the crystals as a function of time and some process parameters like the cooling rate and composition. And such analysis methods seem to be already rather widely applied. In the field of property prediction or materials discovery, which is also relatively developed, I would like to show an example from nitride materials, specifically ternary nitride materials, in which hierarchical agglomeration was used to cluster together metals with a similar propensity to form either stable or metastable ternary nitrides. And this was used to predict the thermodynamic stability or metastability of ternary compounds that are shown in this map. So the position shows the composition, and the color coding refers to the stability that was predicted. And using this method, it was possible to predict a large number of new ternary nitrides. And the authors also were able to validate their results by synthesizing a subspace of those materials already. Now I would like to talk about some examples from the field of synthesis, or in this case, crystal growth, where I have some more insight. The example here is taken from top-seeded solution growth of silicon carbide. So you can see the experimental setup used for this growth technique here, with the seed crystal and the solution. And in this first step, the authors used machine learning for accelerating numerical simulations. So at first they had to gather the training data by running numerical simulations in this domain, which they did with 800, and then extracted data from those indicated points, which were then used to train machine learning models And eventually the machine learning model was validated by another previously unseen 200 CFD simulations. And if you compare the results of the CFD simulation and the prediction by machine learning, you can see the same general trends in terms of the fluid flow and the supersaturation field. And when evaluating this, it's also very important to notice the difference in speed. So the machine learning models were several orders of magnitude faster than a CFD simulation. And this was the basis for the authors to use this method for coming up with an adaptive process control. At first, this uses the previously shown approach in principle for determining the growth rate of silicon carbide, the parasitic deposition rate, and the crucible dissolution rate in a CFD simulation, which is then used for training a machine learning model. And then a second component of this work comes into play, which is an optimization algorithm that was used for optimizing controllable parameters such as the rotation speed of the crucible and crystal, or the position and the temperature. And the objectives was to maximize the growth rate, to reduce the standard deviation of the growth rate, and to minimize both the crucible dissolution rate and the polycrystal deposition rate. And they could show that in all those fields, significant improvements were made by this adaptive process control. Now I would show a brief early touch on data extraction. This can refer to extracting relations, but also extracting data itself, which I think can become very relevant for building comprehensive databases, which can then be used in machine learning also, or other AI techniques. There are efforts in natural language processing to extract data from scientific literature, from all parts of scientific papers, including texts. And there are also a number of existing toolkits, especially in the chemical part of material science. But still, this is not yet really widely adopted, and there's still plenty of room for realizing the potential of this for building the databases. Lastly, I would like to show an example for theory discovery, or in the direction of theory discovery, which is probably the least developed application area. This example is from photoanode material development, where a convolutional neural network is used to predict the photoelectrochemical power generation from composition and from Raman spectra of the materials. And an analysis of the gradients in the trained model was used to identify data relationships and to make automated predictions of the directions in parameter space. So in which direction should we move to improve it? So analyzing interpretable machine learning models is increasingly utilized to find fundamental relationships also. However, so far as I have seen, the interpretation of the identified relationship still seems to be a task largely conducted by humans. Now I would like to talk a bit about challenges. One challenge, I think it was mentioned also in the previous talk, is of course the amount of data or the pace of data acquisition. It depends a lot on what subfield of material science we're talking about. In some subfields, it's possible to implement high throughput experimentation to generate data more time efficiently, or also in terms of investment. In some other fields, it may not be possible to implement high throughputs, and in those fields, better integration of AI and existing understanding-based knowledge will be important, because by doing so, we can narrow down the number of degrees of freedom for a model and improve the model's performance on small data sets. Of course, also the AI compatible data management is something that is still in the process of being adapted. For example, the digitalization of experimental documentation, standardization, and accessibility of data. And I think this will improve naturally as more and more people utilize AI methods or plan doing so. There's another issue sometimes in fields that are not capable of producing a large amount of data efficiently. That is that sometimes the data exist already, or they are accumulated more easily globally, but sometimes it's not possible, or it does not seem possible to share the data or to build a data pool globally. So this is something I don't know the solution yet, but I'm interested what people might come up with. Lastly, the interfaces and the integration of AI tools with existing methods. In microscopy, we already have commercial applications or integration into commercial tools softwares that come with the characterization equipment, and that allow deep learning model training for users that are not experienced in AI otherwise. So this one is just an example. However, there are other subfields where such integration into existing techniques is not yet widely present. So from my personal experience in numerical simulations using general purpose CFD software, I don't see much of an adaptation of the softwares yet to either directly integrate AI or machine learning into such softwares, or to have convenient interfaces for combining those technologies. So, and at the end, I would like to come to the question of what can materials research do for AI in general. So I think for AI as well as other computational materials research, fast computation will remain important, and the demand will be to increase computational power, of course. So this can partially be done by classical computing, but also quantum computing potentially becomes very interesting for this. And I believe that with the growing demand and the growing ideas of utilizing large data sets and complex models, also we will want to have energy efficient fast computation. And for this, I think it would be very interesting if we can realize quantum computing at room temperature or near to room temperature, because much of the energy consumption in quantum computing to date is the cooling requirements. And at this point, the materials platforms become very important again. And for example, color centers in diamond or silicon carbide may be able to provide a materials platform for realizing this energy efficient and fast computation. So I would like to summarize my talk. AI is already widely applied in materials characterization, property prediction, and synthesis. The AI use in materials research is still dominated by machine learning methods. interpreter model and integration of AI and existing domain knowledge are on the rise, but still limited. The quantity, standardization, and accessibility of data remain a frequent issue in some materials research subdisciplines. And materials research itself may become an important platform for general AI applications by realizing unprecedented computational power. So I would like to thank you for your kind attention and welcome your question.
Thank you so much, Sasuke. Very, very interesting. So from your point of view, I mean, where do you see the, how can I say, the biggest potential for AI related with material research, or where do you think, where is the kind of the sweet spot, so to say, from your perspective?
This is a very good and general question. I mean, I think that there's certainly many good opportunities still in the field of materials processing and optimization problems. And certainly automated characterization. I'm not completely sure how far AI will, or how quickly and how far it will get in the theory discovery field. I think this is probably the most challenging thing, and I'm not sure if the potential here is really completely clear yet. So
I guess, I mean, the theory is the most kind of far-looking kind of scenario in a way, right? And it kind of, I think it's the less kind of developed area.
Yeah.
And processing is probably good. Yeah.
I mean, probably your question is how much I expected to develop.
Yes, right. Yeah.
Lars, I have a question, if I
yes,
may.
Paolo. Yeah.
Yes, thank you for the presentation, Saskia. So I had a question regarding the automated imaging that you were talking about. So now we have cameras that take, over 1,000 images per second, or even more. So how you see that this combination with this AI and machine learning in terms of being able to interpret the data at those kind of speeds, so we have real-time analysis.
Mm-hmm. Well, I mean, I think it's generally possible to handle quite large amounts of data and to process them very efficiently. I mean, seeing the speed up for the numerical simulation, I think maybe the speed up or the amount of data handling in image analysis is also quite impressive. But of course, in practice, I think sometimes we may also need to think about what are the data that we actually need. So, for example, sometimes we may not need the full resolution of all images, or we may not need the full time resolution. In this example that I showed, the authors used a higher time resolution at first for detecting, well, to have a rough analysis, and then they used a backward search to figure out when a crystal actually started to form after finding it. So to manage this challenge.
That's good. I mean, it's to discriminate, to reduce the number of data points in a way, right? And then when you find the sweet spot, then you expand again.
Yeah.
And this, of course, I mean, the complexity of data analysis with the fast cameras, as Paolo speaks about, it will be an immense problem, so to say, for the human person to kind of digest all this data. So I think AI here is absolutely crucial, I think. Okay, we need to move on. I'm sorry, we cannot take more questions. Thank you so much, Saskia.
Thank you.
Thank you. And the third lectures today will be given by Alina Adriana Minea from Technical University Asaki. So the title is New Heat Transfer Fluids for Saving Energy in Heat Exchange Applications. So please, Alina, the floor is yours.
Thank you. Okay, just a second. Okay, I think it is okay. Okay, so I am Alina Adriana Mina. I'm coming from Gheorghe Saki Technical University of Iași in Romania. And I am Vice Rector for Doctoral Studies. And today I will present you several things about our research in new heat transfer fluids for saving energy in heat exchange applications. Ultra high performance cooling is one of the most vital needs of many industrial technologies. However, inherently low thermal conductivity is a primary limitation in developing energy efficient heat transfer fluids that are required for heat exchange applications. So because nanomaterials have unique mechanical, optical, electrical, magnetic, and also thermal properties, appeared the new enhanced fluids called nano fluids that are engineered by suspending nanoparticles in traditional heat transfer fluids, such as firstly appears in water, oil, or ethylene glycol. So even if this concept is not new, the term was actually coined by Choi in 1995 to describe this new class of nanotechnology-based heat transfer fluids. The research is still ongoing, and unfortunately, their technology readiness level is not so high. So actually the TRL is lower than 3 in most of the new fluids. But the area is benefits from a lot of research and a lot of publications and a lot of experimental, analytical, and numerical approach, because actually the let's say the interdisciplinarity of the field is very high. So I will present you several things that I, together with my team, worked over the years. And also there is an ongoing project financed by COST. It's called NanoConvex, actually nano fluids for convective heat transfer devices. That is a continuation of a previous project financed also by COST, Nano Uptake. This project is a network. It was a networking one because it ended last year in early 2020, and it called Nano Uptake and gathered around a lot of research groups from mostly from Europe, but also from Brazil, China, India, and Canada. So this project helped us to have a better overview of what is happening with nanofluids and their applications inside heat exchangers. This NanoConvex project with valuable application in convective heat transfer devices aims on increasing the TRL from 3 to 4, and as you can see, is coordinated by Professor Matthias Buschmann from Germany, and also have valuable cooperation, benefits from valuable cooperation also from Portugal and Spain and Italy and so many countries, because it is a COST project, it's a networking one. I will go further on. I will go, let's say, a little bit on a hurry because I know that the time is killing us. And I will shortly talk about nanofluids and basic nanofluids, and after that about hybrid nanofluids a little bit, and ion nanofluids and PEG-based nanofluids, because these were actually the classes of nanofluids that we tried to investigate them as detailed as possible. So nanofluids are based, what we studied were based firstly based on water. And as you can see also in this slide, we added some oxide nanoparticles, and you can see that the heat transfer enhancement was very good. We get up to 8% heat transfer enhancement if compared with water at different Reynolds number, mostly investigated in turbulent convection. Of course, in laminar convection, the enhancement is larger than that, because there the thermal conductivity is much more important. But adding nanoparticles to a regular based fluid, it increases the thermal conductivity, but it also increases the viscosity. So we have to balance the advantages and drawbacks of each case, and also the stability is very important. But I will move forward to a little bit about hybrid nanofluids. And the hybrid nanofluids are a very new sort of nanofluids which can be prepared either by mixing two nanofluids or by suspending different types of nanoparticles, or hybrid nanoparticles, composite ones. There are a significant amount of research in this area, but the main issue was found to be the stability, because adding two kind of nanoparticles, it decreases it decreases the stability of the fluid itself. So I believe that hybrid nanofluids are not a very good solution, at least at this moment. Nevertheless, the use of hybrid nanocomposite was better, and some authors found an increase in convective heat transfer up to 52%. So this is rather good. But the fabrication of the hybrid nanocomposite is a little bit expensive. Our research, just an outline, found that the relative specific heat is decreasing a little bit, depends of course on the composition of each nanofluid. The thermal conductivity is getting higher by almost 22%, and the minimum increase was around 12%, 12 to 13%. But if you look on the relative viscosity, with few exceptions, this is getting up to 3.5 times higher than the base fluid. Nevertheless, we tried to estimate and to look also at heat transfer enhancement at different Reynolds numbers, and here are the results presented for one case. And you can see that the heat transfer enhancement, if compares with regular water as the base fluid, it goes up to around 2 to 2.5. So this is rather good. If we are going to talk about ion nanofluids, these new nanofluids are very interesting, because the base fluid is actually ionic, are ionic liquids. So the key advantages of ionic liquids are listed here, but I want to outline especially the large working temperature range, and the non-volatility, and also their designability. This is very good. and also the environmental protection, because the ionic liquids are actually considered ecological fluids. The preparation of your nanofluids is the same as for all nanofluids, and the most traditional method is the two-step method, when ionic liquid and nanoparticles are mixed together, and the next step being the dispersion. And this can be, and the dispersion can be stabilized by magnetic stirring, sonication, particle surface modification, or surfactant addition. The surfactant addition can assure a good stability. Nevertheless, if we are adding surfactants, the thermophysical properties control is somehow lost. So we have to be very careful if we need the addition of a surfactant. Here in this slide, I tried to outline a little bit some basic properties of some regular oils used at high temperatures and several ionic liquids in terms of density, heat capacity, thermal conductivity, and viscosity. You can see here very clearly that ionic liquids are more viscous than other fluids, but also the thermal conductivity is in a very good range. Here are some of our experiments just to help you to make an idea if what is the enhancement of heat transfer coefficient if you are talking about different ionic liquids with different kind of nanoparticles. So here we have the addition of graphene and multi-wall carbon nanotubes, very low percentages. And here we added alumina. And also there is a comparison with the basic nanofluid, that is water plus alumina. So you can see here that the enhancement of heat transfer coefficient is higher when ionic liquids are used, but I have to underline here that the Reynolds number is in laminar regime, because ionic liquids are very viscous, most of them. Here you have also another plot that can help you see the heat transfer coefficient enhancement over the base fluid. Yeah, here is the base fluid, and this is with addition of alumina and other nanoparticles. You can see here that the enhancement, it goes up to 56%. But depends mostly on both on the ionic liquid that was used as base fluid and also the nanoparticle type and concentration. If go further on with the polyethylene glycol-based nanofluids, this is somehow a newer area. Polyethylene glycol are in the range of phase change materials, but the interest of PEG family as fluids is rather limited, and the research is still ongoing. So we have some interest observation by this moment, and an experiment that is ongoing and delayed due to this pandemic, but our preliminary results are very encouraging. But we have to outline here that we cannot use almost all the PEG almost all the PEG fluids, because not all of them are suitable as for heat transfer applications. So this is also an outline of some thermophysical properties in terms of thermal conductivity, viscosity, specific heat and density for several PEG PEG phase change materials. And of course, the number that appears there signifies the average molecular weight of each compound. So the experimental that were identified in the open literature are limited to PEG 1000, because after that, if we increase the molecular weight of the compound, the viscosity is too much, is increasing too much. So they cannot be used as fluids. So
excuse me, the time is, you have used more or less your 15 minutes already. So can you wrap up very quickly?
Okay. So I will say that I will go to just a few lines about mechanisms. So in general, the mechanisms that are guiding these nanofluids is in regard to viscosity. The addition of nanoparticle increases the viscosity, and when temperature increases, the viscosity is decreasing, as for most of the fluids. In regard to thermal conductivity, it is clear that the thermal conductivity enhancement is very high, and this is especially due to solid nanoparticles addition. In regard to specific heat, the results are contradictory and highly depends on the base fluid, and we have to rely on the experimental values. As overall conclusion, the main application of nanofluids and heat exchange systems refers to overall energy consumption decreasing, and we believe that these fluids are the future for heat transfer fluids. Of course, it is needed to have a more inconsistent theory regarding their properties. So thank you for allowing me to present you some general things about nanofluids.
Thank you so much. So I have just a very short question here. I mean, the heat exchange is, of course, an enormous industrial kind of application and is used widely. And do you have a number how much kind of energy saving in percentage that you would kind of, what would be possible to do by, let's say, the most best fluid that you can even think about that could be designed? What would be what is the percentage savings, so to say?
So we can go, depending on several fluids, it can go up to 40 or 45% overall enhancement, but we have to take into consideration also the costs. So if we want to have a better fluid, we have to spend more money on this. So at the end, we have to balance a little bit the money that we spent on the new fluid and the actual energy savings that we are doing. So this needs a lot of studies, and I can say that most of the researchers that were done by now did not consider also the financial aspect. You know, like every research, everything is fine, but when you have to apply it, you see that you will spend more money on that.
Yeah. How is it with the kind of the green balance, so to say? I mean, if one would replace all exchange fluids in heat to something else, could one exchange that to something that is much more green than what is presently used?
I'm not very sure about the costs for this, but I saw some applications that were developed during also nano uptake, the project that we talk about. They are also on the market. There are some in USA. There are some coolers for computers that requires a little bit of fluid there, so the quantity is small. But at this moment, I will go on recommending it for application that are very high tech and need a small amount.
Low amount. Okay.
Yeah.
Okay.
At this moment.
Oh,
But
okay.
in Spain,
Thank you very much.
In Spain, there are trying to process them at larger scale, as far as I know.
Okay.
Thank you.
Thank you very much. And now we need to go to the next speaker, which is Ehrenfried Scheich from Fraunhofer Institute in Dresden. And his title is High Resolution 3D Imaging of Materials and Integrated Circuits, Enabler for Disruptive Innovations. So please, you're welcome.
Okay, thank you, Lars, for this introduction, and thank you to the organizers for inviting me. It's really a great pleasure for me. And this morning, Jan Rušák made a very important statement from my point of view. He said, research infrastructure influences the whole innovation process. And I would like to provide a particular example which becomes more and more relevant for material science and engineering. It's high resolution 3D imaging of materials. And I will also have an example from microelectronics. And I would like to convince you that this is an enabler for disruptive innovations. And I would like to thank my team, and also I would like to thank colleagues at Intel in Hillsborough in Oregon and 2 institutes in Poland who contributed to the examples that I will show in a moment. But let me start with a more general view on microscopy. I think you all know light microscopy, which we can use with a resolution in the best case of about 200 nanometers because of the wavelengths of the light. And the first microscopes, the first light microscopes were built in the middle of the 17th century. Until this time, it was not possible to see structures that are smaller than about 400 microns. And this was, for instance, Anton van Leeuwenhoek and also Robert Hoek, who made really nice picture. And this first microscopic imaging were able to show us bacteria. And I would like to mention only one example. The light microscope was the infrastructure for Robert Koch to visualize bacteria. And it helped him to understand tuberculosis as a very critical disease at the time. And he established the modern bacteriology, and he is the father of microbiology, got the Nobel Prize in 1905. So this was a real breakthrough. Then in 1931, Ernst Ruska built the first electron microscope. With electron microscope, you can image up to the atomic level, as you know. And this brought a breakthrough in solid state physics and material science and engineering. For instance, you can image dislocations, and you can image precipitation processes in alloys and so on. And it was also extremely important for microbiology and medicine and for microelectronics. Microelectronics is not possible without electron microscopy. But we have a missing gap. And this missing gap is filled by X-ray microscopy in the lab with a resolution today of about 50 nanometers. The first experiment was done by Günther Schmal from Göttingen in 1976. And the essential point is that we can do microscopic imaging of buried structures, of opaque materials. And the first microscopes then used are from the beginning of this centuries. And I think this technique has a huge potential for system biology and medicine, for architectures, mainly hierarchically structured materials, for materials for energy technologies, and of course for microelectronics and particularly 3D structures. That means the uniqueness of this technique is the combination of high spatial resolution and object penetration. Now the question is why it took so long until X-ray microscopy became an imaging technique. There are mainly two reasons. The first reason is the complex refractive index of lenses or of materials. For X-rays, this complex refractive index, is for all materials nearly 1. So therefore, it is not possible to build easily refractive lenses. This was a strong argument that also Ernst Ruska, who got a Nobel Prize for electron microscopy, made. However, there are other possibilities to focus X-rays, for instance, diffractive optics. And one example you will see on the right side, these are so-called Fresnel plates that are systems of concentric rings. However, if you would like to get 50 nanometer resolution, the thickness of the outermost ring has to be 50 nanometers. And to manufacture them is not easy. You need technologies from microelectronics, and they were not available for a long period of time. So we had technological limitations. And these two reasons are reasons why X-ray microscopy is has been only available for a couple of decades. Now here you can see how a laboratory X-ray microscope looks like. Generally, it looks very similar to, from the scheme, like an optical microscope. However, you need an X-ray source and you need also other optics, as I have told you. And for a photon energy of about 8 keV, that's kappa K alpha radiation, you have to thin the sample to about 50 microns. I will come back to this point at the end. And you need particular focusing lenses, so-called Fresnel plates, to get a resolution of 50 nanometers. The lenses are the components that limit the resolution today. X-ray microscopy has really unique features, and it is applicable in several fields, in system biology and medical research and diagnostics. For instance, also in virology, for instance, also to image processes that are connected with the COVID and the attack of the virus to the cell. Another field, of course, is microelectronics, including masks, then fracture mechanics on small scales, a huge potential from my point of view. And last but not least, materials for energy technologies, for batteries, fuel cells, hydrogen technologies. I will show some examples. The first example that I would like to show to you is the integration of a micro double cantilever beam test, a mechanical test, into an X-ray microscope, so that you are able to image the crack during crack propagation. We have done the very systematic studies of crack propagation in microchips for microelectronics. This is necessary because dielectric materials that are used in leading edge microchips have a very low fracture toughness, and therefore particularly guard ring structures that stop cracks, microcracks, have to be established. You see on the left-hand side two situations where you see the crack that is propagating in such a microchip. In the middle, you can see the crack opening in situ. And on the right-hand side, you see that the critical energy release rate at a particularly designed structure, this is the blue part, this is the guard ring, is increased by more than a factor of 3 in microchips that are developed today. So that's a huge advantage for microelectronics, but for material science, we can say we are able to determine the critical energy release rate or the fracture toughness of materials in a range of about 100 nanometer. That's completely unique with X-ray tomography and provides a huge impact for the interpretation of fracture mechanics. Another example that I would like to show is fracture mechanics on small scales. Here in the case of mollusk shells. Mollusk shells are designed in a way that the cracks are steered into toughened regions. So such a mollusk shell is a composite between crystalline materials, that's a calcite phase, which is extremely stiff, and between the calcite, there's an amorphous organic component. And this organic component is the component that stops the crack. That means at first, the cracks have to be steered into the organic component, and then the crack is stopped. Very clever process from biology, made in evolution. And I think I'm convinced that this better understanding of these processes also by in situ nano-XCT studies will help us to design completely new engineered materials that are hierarchically structured similarly than materials in biology. The third example that I would like to show is from energy technologies. Electrodes for batteries have a high open volume. These are porous materials. And from X-ray tomography, it is possible to determine parameters like porosity or parameters that characterize the interconnectivity of pores, like tortuosity. And these parameters can be used, if we determine them experimentally, for fluid dynamic modeling to improve the morphology of battery electrodes. And here you can see how such a nanotomography looks like. Another very important application for battery engineering is to study materials that are resistant against microcracks. Because of phase transformation and volume changes in the battery materials, after a certain amount of cycles, it is typical that microcracks are formed and that then they are propagating. And if they are propagating, the performance of the battery goes down. So therefore, it is important to understand these processes, and we are able with X-ray tomography to image such microcracks also in operando. Now, at the beginning, I said that one of the limitations of today's laboratory X-ray microscopy is the energy of the photons used with 8 keV, and consequently the thickness of the samples that have to be, of course, depending on the materials, in the range of 50 microns. If we use higher energy, maybe 17.5 keV molybdenum K alpha, then the samples can be millimeters or centimeters thick. This is an important advantage. No sample preparation, larger volume for in situ and operando studies. This is only possible with new optics, so-called multilayer Laue lenses. And combining multilayer Laue lenses and new sources together with 3 companies, Sigre in US, Axo Dresden, and Huber in Bavaria, 2 Fraunhofer institutes, we have built up a prototype of a tool that we are planning to commercialize in Dresden with DeepXScan GmbH, a new startup. At the end, I would like to say that I'm very much looking forward to continuing my collaboration with my friends in Portugal at several universities, but particularly at the Uninova in Lisbon, and also to participate in the new cluster. It will be very exciting for us. However, we are offering to collaborate with all of you in the field of X-ray microscopy to provide research a new perspective and to enable new disruptive innovations. In Dresden, in Germany, we have a long tradition starting in the beginning of the 17th century with Ehrenfried Walter von Schirnhaus, by the way, one of the co-inventor of the Meissen China, who developed new focusing mirrors and lenses and developed them further. Then in the first half of the last century, we had Manfred von Ardenne in Dresden, one of the pioneers in scanning electron microscopy. And then after the Second World War, two important schools with G.R. Schulze and Alfred Recknagel. And now we are continuing this tradition. Dresden is a high-tech hub with a strong network in material science and in microelectronics. And we have a smart and motivated team. I would like to thank you very much for your attention. And if there are questions, I will be happy to answer them.
Thank you so much, Ehrenfried, for a very, very inspiring discussion about possibilities for the X-ray microscopy. It's very interesting. I have one, we are a bit late in the program, but I take the opportunity as being the moderator to ask you one very small question. So, and it relates with the deep scan. I mean, the new deep X-ray possibilities to probe deeply. Is that done also in a kind of confocal level that you can do layered composition? So you can kind of tailor where the focus will be, so you can do a 3D mapping in a deep way?
Yeah, so there are several, at least there are two general ways to go. One is tomography. This is the standard way to go. However, if you have 2D systems that you would like to investigate, for instance, microchips and microelectronics or paper that you would like to study also, then it's an advantage to do laminography. And then in principle, you can, in each case, also in tomography, it's possible to have, and this is deep scanning, yes, in each level, a virtual two-dimensional image. Yeah.
Okay. Yeah, very nice, very nice. And then a comment maybe from your side about what we discussed before about the utilization of AI for analysis of all the data being captured in the microscopes of today, because it's immense amount of data, right? So can you just comment from your perspective about that?
Yeah, of course. This is one of the key topics we are working on. Unfortunately, in 13 minutes, that was my talk, it's not possible to talk about all, but artificial intelligence is extremely important. And also Saskia's talk was excellent, and we are working in similar fields, but we have to make it much more customer friendly also to use it. And this is one of the tasks we have on our agenda.
Okay, thank you so much, Ehrenfried, again. Thank you.
You're welcome.
So we are a bit late, as you all understand. So I will introduce directly Beatrice Fraboni from University of Bologna, who will speak with us about organometallic materials for detection applications. So please, Beatrice.
Good morning, everyone. Shall I start sharing my screen? Can I override?
Yes, you can.
I'm going. So thank you very much for inviting me, and I'm happy to be here today to be able to tell you what is the research that I am carrying out, that I've been carrying out in the past years, together with my research group, of course, at the University of Bologna, and together with many collaborators on organometallic, that is organic and hybrid materials that can detect high energy radiation. When I talk about high energy radiation, I really mean X-rays, gamma rays, and I will show you briefly, we're also trying to deal with charged particles. So definitely not visible photodiode. Why we need high energy radiation detectors is obvious. We know that high energy radiation is everywhere, can be very harmful, even though can be also very useful in medical applications. But the good question could be why? do we need novel advanced material for this task that has been carried out for many years quite successfully? I try to summarize in this slide what are the major pros and cons of state-of-the-art commercial and research-grade inorganic materials used for radiation detectors and radiation detectors in general. As you can see, they both have quite a lot of pros, but the major cons are that it's very difficult to have flexible detectors with the given technologies in inorganic materials, and it's very difficult to have them scalable to large area. So the need for large area detectors, possibly also flexible to conform to large area surfaces, has become a very important need and cannot be fulfilled by the existing inorganic inorganic radiation grade materials. So we started working on materials, and typically organic and perovskite and hybrid, that could grant the possibility to be deposited over large areas, maintaining a good detectivity for radiation, which is not trivial, and that can be also deposited at low temperature, therefore over flexible substrate. That, of course, also implies using or targeting materials that can be operated at low voltages, because if you want to go for for wearable applications, but again, also for large area, that means a lot of pixels applications, you cannot really rely on 1,000 volts, which is what is typically used for medical diagnostic detectors at the moment. Very efficient, super accurate, but again, they have a few drawbacks. So the material platforms that are very promising are organic, semiconductor, perovskites, and high mobility amorphous oxides. These are all materials that share the possibility of being deposited from solution at low cost with relatively low tech, well, quite low tech technologies and processes. And that is very important for the applications we are targeting. These materials also share the properties of being electronic grade materials. So they're all capable of transporting charge and being already structured in electronic devices. What kind of device do we need to detect radiation? We can have two approaches, indirect and direct. We will focus on the direct detection mode that foresees the direct conversion of X-rays photons into electron hole pairs, therefore into charge carriers that can be directly collected as an electrical signal. Okay, so today I will talk about direct detection processes. This view is quite full of information, but I wanted to show you the steep increase in performance of organic and hybrid materials used for the direct detection of high energy radiation. So we're not talking about solar cell, no photodiodes, but really high energy radiation detectors here. What is the figure of merit on the y-axis is the sensitivity, which is one of the most important, not the only, that is used for characterizing the performance of radiation detectors. In orange, you see perovskite. In blue, you see organics. You definitely can notice the strong and steep increase, both in the thin film or in the single crystal form. They're both very interesting, as you can imagine. Single crystals can be grown in thicker dimensions, larger volumes that allow a better absorption of the radiation because it's hard to stop high energy photons, but it's also harder to scale them to large areas. So there are pros again and cons also with single crystal or thin films. And today I will focus more on the thin films, but there are very good results also on the single crystal form. Another important message is these two dotted lines, the red and the black one, that represent the state-of-the-art sensitivity value for inorganic large area detectors based on polycrystalline CZT, cadmium zinc telluride, or amorphous selenide. So you can see very, very clearly that we are already way beyond the state-of-the-art with, of course, at the moment, research outputs, research results, both in organic and perovskite materials. Now, let me focus very briefly on how are these organic thin film detectors made. Well, they're basically simple organic thin film transistors fabricated onto flexible substrate in the bottom gate, bottom contact geometry. I'm here reporting one geometry, but it's not the only one. We can also have different geometries, and actually that would be a very important parameter to play with to improve the performance, but also two-terminal device sometimes can be used. So that is a typical example, a good and well-performing one, where you see that the organic semiconductor is very thin, really about 100 nanometer thick. How do we deposit it? We tried different techniques with success. So nozzle printing, bar coating, bar assisted coating, and they all provide very good results. So it is an easily transferable and scalable deposition process. What kind of organics? We use different molecules. Today I will comment a little bit more TIPS pentacene, which is a very standard and common molecule in organic electronics. And I would like just to focus the attention also on the TIP germanium pentacene, the one next to it, where the only difference is the substitution of the silicon atom with a germanium atom. Why is it interesting? Because you will see in the next graph that by simply changing the atomic number of one atom in the molecule, we can increase the absorption of high energy radiation of the material and therefore improving the performance. So that is what a typical 20 pixel matrix looks like, fabricated, as you can see, on a flexible PET substrate. Each pixel in this case is a very simple interdigitated source drain structure with a bottom gate dielectric, and the film has a polycrystalline form. The quality of the material is very important because the big question is, how can a material which has such low Z elements be able to stop in 100 nanometer high energy photons? That is a good question, but let me go first to the other advantages of using such a low Z material. First of all, it has the density of human tissue. So it is human tissue equivalent, and this for medical dosimetry is fantastic. Second, it does indeed absorb very little radiation, but on the good side, it has a very strong radiation tolerance. So the radiation damage is very poor because really very little amount of energy is deposited in the material. So why is it sensing and detecting radiation at all? Well, what sets in is a photoconductive gain effect that consists basically in the selective trapping of one of the two charge carriers produced by the impinging high energy photons. So the photo-generated carriers get partly trapped at defects that have to be present in a controlled way. And there comes the strong knowledge and skills on the material, because in this way, by properly tailoring the defective states, one can modify the carrier lifetime and the transit time in the device, and therefore acting on this G factor, which is the gain. This gain has a very important role in enhancing the delta I, which is the photocurrent induced after or during the exposure to X-rays. So you see here reported an on-off response of the material I was showing you before, the device I was showing you before, to a 40 kilovolt X-ray beam. You clearly see that the material provides a strong delta I, reproducible, and the different curves refer to different dose rates, so to different fluxes. What is interesting is that by playing with the device, transistor or other geometry that we decide, by playing with the printing procedure, and namely with the morphology, defective states, polycrystalline grain interfaces, we can affect the charge transport and collection properties. And by playing with the material, the molecular structure of the organic film, we can enhance the radiation absorption. So that is only possible because we are using these organic materials that are so versatile. And the same holds also for perovskite. I will just show you the results for perovskite. The message here is that you see a very nice linear slope, linear response that tells you that these materials can be used as actual dosimeters in real time. The operating bias is very low, about 1 volt. The sensitivity is really good, beyond the state of the art, as I was showing you in the beginning, in the review graph. And here, what I wanted to show you is how the slope, which is the sensitivity, changes by simply changing 1 atom in the TIPS molecule. So again, these are the first results, but I think this opens a very nice perspective for future advanced material development. One more comment is, by using a very simple 2-terminal structure here, not even a transistor, we were able to detect protons. And having a flexible, very simple device that can detect protons of 5 MeV is very important for proton therapy, for example, but also for other space applications, for dosimetry for astronauts, for crew members. What is also interesting is that, again, what we are playing here with, I'm not giving you too many details, is the material and the interface with the substrate. So again, a lot of work on material to grant both real-time detection and, in this case, integrative mode detection by using the plastic substrate as a charge reservoir that keeps the history of the irradiation of the device. So just to move to perovskites, they are also very popular. There's a lot of knowledge in the scientific community about solar cell perovskites. So we decided to basically rely on all this knowledge, and we slightly modified solar cell structures that were already fabricated to be, as you can see in the image, ultra flexible and ultra thin. So here, what I'm showing you is a device which has the same perovskite, which is an organic CS-PAMA perovskite. I'm sorry, I haven't reported the formula. And we have played around with the other layers, with the other heterostructure layers. Why did we do that? Because we wanted to see the effect of the interface in the radiation collection in such a thin structure. And the output was really interesting, because you see that even if we have the exactly identical perovskite thickness and material, by changing the interfaces of the electron and hole collecting layers, we really change enormously the 3 major figures of merit for high energy radiation detectors. Of course, I'm talking about that now. So the sensitivity, the dark current, and the LOD, which is the limit of detection. So what I'm trying to say here is that you can tailor the performance of your radiation detector very easily, because you might not always need a high sensitivity or a very high LOD. It depends on the application. What is also very important here is that these devices operate at 0 bias. So they are fully passive, because the depletion region in the thin layers is enough to fully collect all the generated charges. So that is very important, because here I'm reporting, just for example, 3 different structures with, again, same perovskite, different heterostructures. And you see that under the same X-ray beam, the response on-off is very different in terms of intensity, and therefore also the sensitivity, which is the slope, varies strongly. But again, these are very good because they are 0 bias, fully passive. So very good for large area and very good for wearable applications. Last information I'm giving you today is that you don't need such a complex solar cell heterostructure to have a good thin film perovskite detector work. Here I'm just showing you a 2-terminal device where the active layer is a thin film, in this case of a blend of perovskite and polymer. And you see that the response under on-off beams, X-ray beams, in the range here, I'm just reporting the 150 kilovolts, but it goes all the way down, is really reproducible, operating at low bias and very reliable. So again, the focus here is on the material. And I think that really what we can, there's a lot that we can do on playing with this material that allow to obtain, as you can see, very nice linear response for dosimetry. So to summarize, we have reported the recent results on perovskites and organics used as direct radiation detectors. The references are reported in that reference. I didn't report all the papers, but you clearly see that we are really well beyond the state of the art in organic large area materials. And therefore, my conclusions are that I think there's a lot that we can still do as a advanced material community in studying, inventing, or improving the materials that we have at hand to develop novel radiation detectors. I think that really both organic and hybrid can be very, very promising because we need electronic grade materials. And the fact that we can work with deposition from solution also allows this technology to become widespread and really to extend their application to a lot of different areas that go beyond the high-tech, quite expensive ones. So I think I would really stop here and thank you very much for your attention.
Thank you so much for this very interesting presentation, Beatrice. Very, very nice. So I don't see any questions from the audience right now, and we are a bit behind in the schedule. So I think we go to the next speaker, sure. Right? So, okay.
Rodrigo, to make a comment, if it is possible. Yeah. Is the following. I apologize all of you because during the morning section, the commissioner tries to go in and she could not get in. And now she sent to us the video of her presentation because she is moving from Brussels to Portugal. And we will pass the message from the commissioner this afternoon. I'm sorry for this.
Okay, okay. But it will be after lunch, right?
Yes. Yeah,
okay, very good. Okay, so then it's time to hear a bit perspectives from the industrial community. So we are happy to have Pedro Bernardo from Bosch in Portugal that will speak with us about embedded electronics and smart material. So please, Pedro. Oh, Pedro here. If you are here, you are muted still because I don't hear any sound.
He is in, but he is unmuted.
Okay. So can you unmute, Pedro?
Acho que precisamos que a organização faça o unmute.
Nós já pedimos, mas ele tem que aceitar. I
Pedro,
already sent him the message.
You have to accept the message that was sent to you.
So I just want to say one last thing, which is to give you an idea of what they're going to cover in these evaluations.
Ponho a outra pessoa que está aqui, é o Carleo.
They are procuring a large number of studies, 16 major studies, and one of them is focused on excellent science. So that's the one.
Someone is speaking in the background, but I don't know if that is Pedro or if there is someone else. But there is no slides, at least. Ah, here we have, now this is Carl. Hello, Carl.
Hello.
I see you now. Maybe we should take Carl's presentation before and then go back to.
Yes, and maybe we go for, I don't know. The point is that it's just to see, maybe someone wants to see Carleo presentation. On the time schedule. Okay.
Yeah, okay.
I think we can because it's over time. Yes, do it.
Yeah. Okay, so please let me introduce Carl Leo, head of the Institute of Applied Physics in Technical University in Dresden. So, and he will speak about flexible organic electronics. So please, Carl, the floor is yours.
Thank you, Lars, and thank you, Rodrigo. It's a pleasure to present here at this very interesting meeting. I hope you can see my slides and hear me well. If not, please tell me. The original title given was flexible electronics, but that's a very broad field, so I'll mostly talk about organics, and we've just seen this beautiful results from Beatrice, where you've seen one specific application, radiation detection. I'll go a little broader. Well, why do we need flexible electronics? Obviously, there's an interest in devices which are robust, first of all, but also foldable, rollable. We need simple and low-cost manufacturing techniques for flexible electronics. Obviously, because nowadays silicon fabs are multi-billion fabs, but it's clear that there will be many new applications in consumer, healthcare, and so on. Therefore, it's of high interest to drive this field. When it comes to flexible electronics, there are a number of technologies. The most historic one is the morphosilicon, which has been developed many years ago and is used in many products. There's excellent work on thin film oxides from Rodrigo and Elvira especially, and many others, and these transistors work exceptionally well. But another alternative is organic semiconductors, and I'll make a few points where these organic have some specific advantages. But overall, I think it's important to state that we should always pick the best materials and shouldn't have any ideology in selecting materials. Now, what about organic semiconductors? I don't want to spend much time on it. On the right, you see some of these molecules, and both molecules you've seen in your everyday life. If you have some blue plastic container, usually it is of phthalocyanine as color. And if you see a red car, very often also it's painted with perylene. But when you prepare these materials on thin films, which works on almost any substrates, you can do very nice applications like organic LED, photovoltaic cells, transistor and memory, and more. And maybe a most important point is that the number of material you need for a square meter of device is very, very small. For 1 square meter organic solar cell, you need less than 1 gram of these carbon-based materials. Commercially, there is a big success, and this is here the small molecule OLED display for smartphones, which is now a $30 billion market and quickly growing. Also, OLED television is quickly entering the market. OLED lighting is more a niche product. It's in some car backlights, but cost is still a big issue. And I'll briefly mention organic photovoltaics, which is just entering the market. Mainly, I will speak, however, about true electronics. That means transistors and their applications. And there, a commercial breakthrough has not been achieved. Let me say a few words about OPV, because there are really exciting days now. We spent many, many years at the university going from here, little samples, to here. This is a pilot module from Heliatech. It has a 30 centimeter web width and it's all-to-all produced. And there's now the first mass manufacturing worldwide opened, and products are coming on the market. This is one example. This is a storage facility in Duisburg. And the simple point why organic photovoltaics is the best choice here is weight. You cannot put any heavy weight on these facades, but you can easily put very lightweight, flexible modules on it. And the way you do it is actually very simple. You take sticky tape. Now, as said, I wanted to talk about transistors. And you also know that silicon has made an unbelievable development, summarized by Moore's law. We talk about 5 nanometers, 3 nanometers technology. This is really amazing what is working today, and the parameters are outstanding. We are almost at the terahertz frequency with silicon transistors. So now let's look at organics, and the picture is very disappointing. You know, in the last few years, there were a number of results in the tens of megahertz range. Recently, a more encouraging result from my Iranian colleagues at 160 megahertz. But we are still tens of thousand times slower than silicon, although the mobility of these organics is actually only about a factor of 10 or maybe a little more than 10 lower than silicon. And I want to show some examples where we could improve this a little bit by actually starting with a very old device you've seen in your grandfather's radio, the triode, where you control a current with a grid in vacuum. But you can build this also in organic transistors. And the main point is that you can do this in very thin layers, this electron transport here. And you have a very short channel device, which is extremely simple to produce. This was driven by many people in my group over the years, Markus Klinger and Hans Klemann, Felix Dollinger, Axel Fischer and others. And how does the device work? Well, you have here a C60 layer where you inject electrons. Then you have a base contact where you apply the control voltage and you control the current to the collector. To make this work, actually, you need to have some transparency in the base. This means this base has to have some holes, which is achieved by putting it under air where it forms little aluminum oxide covered crystals with some holes in between. You can see that in electron microscopy that there are small holes and the carriers go through these holes, and that works actually very efficiently. So they are pulled down by the field, then they diffuse to an opening, and then they are pulled to the collector down here. And these devices are now exceptionally well operating. We have on-off ratios of 10 to the 7. We have differential gains of 10 to the 5, which means that the base insulation is almost perfect. There are no electrons entering the base anymore. They all go the way they should to the collector. And in terms of subthreshold slope, we are close to theory, and we have achieved very encouraging current densities. In pulse operation, these devices with a few volts work at a kiloamps per square centimeter, which means that you can, for instance, drive a high brightness OLED display with a very, very small transistor. And with these devices, we've now achieved speeds which are already 40 megahertz, and this at quite low mobility of 0.06. This can be increased by a factor of 100, and we expect that this can be scaled much further. But the key point is not to stay in the megahertz range. The key point is to reach much higher values, and recently we've made major steps towards that in work mainly driven by Michael Sawatzky and Hans Klemann. And the idea is here to still use a thin film device, but with highly crystalline organic films, and therefore achieve much better properties. We are using an idea developed by some Korean researchers that rubrene, a specific organic material, grows epitaxial, quasi-epitaxial, by doing some annealing on a thin film and then growing epitaxially. And what we could prove is that you can grow complex device stacks, including doped layers, using this technology. And the doping increases conductivities by orders of magnitude, and still we achieve quite high vertical mobilities of about 10. And we've used this now for first devices, in this case a simple PIN diode, and we measured together with our colleagues in electrical engineering the speed of these devices, and the really very promising result is that we achieved a speed of several gigahertz. And we expect that not only diodes, but also transistors can work at this speed, and opens completely new possibilities for flexible electronics. However, another point I want to make is that organic flexible electronics is based on carbon-based materials, which is closer to the biological body than other materials. And furthermore, you can actually operate these transistors also in an electrolyte. You can use the electrolyte here to gate a polymer transistor. This is the so-called organic electrochemical transistor, which is known actually since many years, invented in 1984. But in the past few years, these transistors have been dramatically improved. This is a very simple example of such a transistor. Basically, it's nothing else than a little p-dot polymer, conductive polymer layer between the source and the drain, and by contacting an electrolyte on top, you get this, as you see, a very low voltage operation of this device. However, recently, my student Matteo Cucchi found a very interesting property. He showed that you can grow these polymers also in an electric field. This is shown here. When you have this contact here, you can actually grow from solution, from monomer solution, such p-dot fibers. And when we saw these photographs, and when we saw the photograph of a neuron in the brain, we realized that this really very much looks like a neuron. So the immediate idea is now, is this a very simple model for a brain, for the neurons and the synapses in the brains? And the answer is yes, to a certain degree it is. The key point about these synapses is that they show plasticity, in other words, learning on different timescales. When you drive them electrically, you increase, so to speak, the connection, and next time you have learned something. And when you stop driving them, you are also forgetting. And on all these timescales, I don't want to go into details, we could nicely indeed see this learning and forgetting. And recently, in collaboration with the Microscope at TU Dresden, we could use these polymer fibers for another neuromorphic application. This is so-called reservoir computing, where you have a nonlinear reservoir and you enter data with some input contacts, you get an output vector, and then you do a transformation of this output vector and classify this way different input vectors. Here is a characterization of the nonlinearity. You see that when we introduce certain frequency, we see harmonics, which nicely shows the nonlinearity. And Matteo was using this reservoir for an actual calculation. We took electrocardiogram data from the web, a data set which has different types of healthy and unhealthy signal shapes. And using this extremely simple few polymer networks, wires, he could actually classify this electrocardiogram, and this would be a very useful device if this is commercially applied. So I think that organic bioelectronics has a huge potential application future, and there are many devices on the body or even in the body we don't think about yet. So to summarize, I think flexible electronics is a field with a great future. There will be many new applications in the future. And one specific point is that organic semiconductors, first of all, have the nice property that they combine good electronic and optoelectronic applications, because they are also good light emitters. And they are also an excellent material for bioelectronics because they are carbon-based, they can work in electrolytes. Finally, I'd like to thank the many people we did this work with, and thanks for the invitation to this symposium, and thank you for listening.
Thank you so much, Carl, for your very interesting presentation. Indeed, I think the organic electronic is very important for the, let's call it, more personalized kind of electronics that we will have in the future, which is kind of not the full major gigahertz kind of silicon electronics or silicon replacement electronics that goes in the big applications, but for everything that becomes more personalized. And I think organic electronics has a big potential there, and there are a lot of things not yet been kind of explored in that direction, right? So I think it's very nice. It was very nice to see your presentation. Thank you so much. I don't see any questions from the panel directly, so I think we try to get Pedro on board since we are a bit delayed. So thank you, Carl, again. And then see Pedro Bernardo, are you here with us from Bosch?
Okay.
Hello.
Finally.
Pedro. Welcome.
Okay, so complicated software issues. Okay, so I will just share my desktop here. One moment. I just have to see which one it is.
So while you do that, I just introduce you once again. So Pedro Bernardo from Bosch in Portugal, and the talk is about embedded electronics and smart materials. So you're most welcome, Pedro.
Okay, so
Yeah, we see it.
you're seeing desktop. Okay, all right. So first of all, thanks for the invitation. So I'm presenting Bosch Portugal on behalf of Mr. Carlos Ribas, that is not able to do so today. And yeah, so the topic at hand is embedded electronics and smart material. First off, I'm at the company, so we have an open space. And therefore, the reason why we have these COVID measures and, of course, the masks. So apologies for that, as the former colleagues did not have. So, but yeah, it's understandable, I think, during the circumstances. So topic at hand, embedded electronics and smart material. Also, to give an overview of we Bosch, let's say, as more of a second-tier supplier to OEMs, what our, let's say, vision or what our intentions with these type of applications could be. And to start off, so some institutional, let's say, slides. So basically our business sectors. So where we are contributing to, starting with the mobility solutions. And here is where I am physically, let's say, contributing, and also, let's say, in terms of region to Braga, to mobility solutions, where we have powertrains, infotainment, instrumentation systems, sensors, connected vehicles. So mobility solutions is the former car multimedia, let's say, part of Bosch. Industrial technology, so for the industrial environment, energy and building, for, let's say, heating and also infrastructure, and consumer goods, which most of us, if not all, have a certain Bosch product at home, be it for do-it-yourself or household applications, as in the kitchen. So facts and figures. So basically, just to give an overview of the associates at each location. Braga, as mentioned, so the mobility part of Bosch. So we have approximately 3.5 thousand persons in here at this plant working. Of those, 467 are directly linked to R&D, as myself. And on the lower side, so just an overview of the numbers. So 1.6 billion euros in sales. And yeah, we are in total 6,000 associates here in Portugal. Brief overview of portfolio of products. So infotainment, as mentioned, so part of the mobility solution. So here our products are tailored or most focused, let's say, to give information to the user or to the driver in this perspective. So a lot of driver assistance and navigation, and also, let's say, in-vehicle computers. On the center part, professional systems, more tailored to the truck and coach divisions, although also linked to the telematics, linked to infotainment. So also a lot of information there. And on the foremost, let's say, right-hand side, instrumentation systems, so clusters. Also an information system, if you can call it that. So it's something that gives all the necessary warnings and information to the driver, and also projection systems as the HUD, so head-up projection systems. And then to sum it up, so connected control units. So these are the units that typically are throughout our vehicles, and they receive, let's say, the necessary inputs and give the outputs to our, let's say, display systems or infotainment systems to give, let's say, the necessary information at the right time to the user. In the central, so two-wheelers, a new, let's say, market opportunity here, or a new, let's say, customer for the two-wheelers. So here also a trend to go with the fully digital infotainment and information systems. And to end, so built to print. So typically our service, we have provide a service in order to, let's say, produce certain products that are not, let's say, related to any of the main domains. as any other, let's say, supplier for OEMs, so we are supplying to the majority of OEMs. And on the lower side, you can already see, let's say, some leading two-wheeler, let's say, OEMs or customers. Moving on to the topic itself, okay, embedded electronics. So why? This would be the why do we need these embedded electronics as part materials? Well, to be simple, our future or the new future will be highly autonomous. So we are going in direction level 4 and level 5 vehicles, where we as a driver will become an occupant and basically a passenger with lots of free time. This will make that, let's say, our car space will be a third living space that we have heard so many times. Where our first living space will be obviously our homes, second living space, our offices. And to really take advantage of this third living space, we really need to, let's say, think a bit different. So we have to rethink and redesign the automotive interior, thinking of how we could really optimize this third living space to make it a more proficient environment for the persons that are commuting. In particular, let's say the HMI trends are moving towards a seamless integration of the above systems that I mentioned. So infotainment and information systems will have to be integrated seamlessly within the cockpit in order to make this a very motivating and exciting experience for the commuter. So in other words, we will be transforming these interior surfaces into surfaces that will be live interfaces. So we will be able to interact with them. And this, let's say, has huge potential, especially in services where we think of shared autonomous vehicles and even, let's say, service providers like Uber or Lyft, for instance. Okay. And what we're going to do with this, or with these embedded electronics? So basically, we will be taking advantage of the large areas available to the occupants. So if you think of our third living space or our interior of our vehicles, we have huge center consoles, huge panels that can be door panels, can be the backrests of seats that can be in fact printed, let's say, with the interactive features. With, let's say, material that can be sensing, material that can be actuating or displaying. So really to make everything that can be reachable and touchable interactive. So application of smart materials together with printing processes like screen printing, inkjet printing, to structure multi-layer surfaces in order to, let's say, to bring these additional functions to the user. And here are just some main examples, let's say. So integration of these multi-layer functions into vehicle interior, so into woods, into leathers, into plastic. So not only are we thinking of just having a simple, let's say, acrylic material with a capacitive screen behind that we typically are used to our cell phones, but really looking into other materials. So the wood, the leather, which are unique materials, that are materials that give a certain, let's say, comfort to a third living space. Those should also be, let's say, able to be smart and to have embedded electronics. So we want to provide, let's say, surfaces that will be able to detect position, force, provide haptic vibration, and even visual, let's say, information like the illumination. One trend now that's coming up very strongly is the anti-microbial polymers. So this COVID situation has, let's say, bring upon us, let's say, a different way of interacting with surfaces. So we have all, for sure, more than once per, let's say, hour, disinfected our hands, because it is now the norm. And this brings a new, let's say, ball game to, let's say, these type of polymers and these type of materials in coatings. So how to really transform them into safe, let's say, touchable surfaces. And this, together with the self-healing materials, so materials that can self-repair themselves, with even internal or external, let's say, stimuli, are two, let's say, main topics also that we begin to think about and want to dig a little bit deeper to implement them and how to, let's say, introduce them, integrate them into our products, because servers, shared autonomous vehicles, which I mentioned before, will be definitely one of the main mobility drivers in the future. And when you think of shared, we have to take care that that the materials themselves, the surfaces themselves, can be, let's say, prepared in such a way that they are safe to be used and are in the same, let's say, form or factor as a previous user. So this is something that we also need to look into. Okay, and how do we go about this? So it's very nice, let's say, saying that we need this and that, but to really go about it and to implement it into our, let's say, products. So there are fortunately already some developments in molded electronics where we have, let's say, some contributions and are developing some products with this. So basically, it's the thermoforming of a film, let's say, printed decorations onto a substrate and then molded or over molded into a mold where we can, let's say, have these additional functions. Another tendency would be the MID, which basically you would have also laser direct structuring in order to perform these circuit diagrams and to have, let's say, this possibility to have components then, let's say, inserted into this. But all this is, let's say, state of the art, and it's been developing for several years. And although we have already some proof of concepts, we really have, let's say, seen a lot of things happening in fairs like CES and even, let's say, prototypes available. But there are still main challenges. So the adaptability of such films, of such concepts to 3D surfaces is still, let's say, one of the main concerns here. When we think of the interior of our vehicles and what we want to accomplish in the future, we are really looking into very, let's say, 3D form surfaces, and some work still has to be done here. Reliability, especially for automotive. So we know that the automotive industry are very harsh when it comes to reliability. So certain climate requirements, mechanical, let's say, vibration, and even the need to have a material sufficiently robust in order to not wear off over time, because these are surfaces that will always be touched and interacted with. So automotive standards are quite high, and we typically see, let's say, the electronical consumer standards trying to be used here, but we really have to go for these automotive standards that are much more stringent. So it's still a complex process chain. So it's not straightforward. So there is still a lot of development to be done and a lot of process adaptations and fine tuning to get to the final product. And of course, the in-molded electronics, let's say, still requires deep knowledge with regards to material and processes. So it's not something from an engineering perspective that is easily done. Although we are working on this, and we have, let's say, some concepts, and we're developing some concepts on this. But in order to enable this, and this is where the innovation part comes in. So we, as Bosch, by ourselves, as engineering centers, we cannot, let's say, develop everything and investigate everything. So we really rely on and depend, let's say, on partnerships with, in this case, with the University of Minho, so a very local university that we have, let's say, several programs up and running in order to address these mega trends, address these, let's say, new technologies. for instance, the PhD program, where we have PhD persons, let's say students, really focusing on the industry, focusing on the processes to make these products viable. The Bosch Academy, where we try to tailor, let's say, certain courses, certain disciplines in order to address certain processes and also give, let's say, our engineers and also the academia, let's say, the possibility to investigate and go deeper into this type of topics. At the center, so development of Portuguese suppliers. So this is a very good initiative because it does not help at all, let's say, to investigate a lot and to really understand how things can be implemented if at the end you cannot find a company, a supplier that's able to produce such components, produce such products. And here we are co-promoting this with universities in order to, let's say, get our suppliers, local suppliers, up to speed, let's say, with these trends and these tendencies. And of course, we have DTX, so digital transformation collaboration, also with external entities, and university, and a prototyping, let's say, lab, in order to help us to develop proofs or concepts in order to, let's say, to prove and to test our products. And yeah, this is what I have. So very brief overview, so not very deep as our former colleagues presented. Nonetheless, open to questions if we still have time. Okay, so thank you from my side once again.
Thank you very much, Pedro. I think the perspective from Bosch is very, very important to get to the conference, and it's fully understandable. It's not so deep as this other scientific presentations, right? But it gives the basis for why there is a need for the science, and I think it's very, very important. And I enjoyed it immensely. So let's see if there are some questions on the chat. It seems not to be. So let me ask you one thing about the how do you foresee what will be the kind of next generation after this? I mean, it will be the third living room for sure, and we'll use the different surfaces, right? And then you spoke about the antimicrobial kind of, now in the COVID post-COVID scenario, people are more afraid about touching surfaces, etc. Right? So I think these are interesting new kind of avenues for introducing new ways of making sensor structures in the surface, either that transmit to you or that you communicate with them.
Correct. Yes.
Right. But do you see something more about this? Because I mean, the kind of digital architecture, if you call it like that, I mean, the architect of the car, it's still a car that you will go into and you will be transported principally. And during that transportation, you can do things. But do you see about these things? Have you some ideas what are these things? Because right now we say, well, we can do technologies, screens, sensors, different things. But do you have any idea about other things that you would like to have in the, let's say, the cockpit of the car, or in the dining room of the car? Would you, for instance, think about 3D printed food that you print during your traveling, so you can eat there directly, like a microwave oven, but the 3D printing food instead? I mean, do you have these things like
3D
that
printing
in
food,
mind?
I would not say 3D printed food, but we have not thought of that yet. But definitely, let's say, to use the automotive, let's say, as not merely as a point A to point B, but really to interact with what's around you. And for instance, being able to see, and this is where IoT comes in, and all the Bosch products being connected to the internet and to the cloud. So being able to see what's in your fridge, for instance, and preparing your meal from your car, already getting, let's say, Amazon or your local grocery to send you food via drone to your doorstep or whatever. To get publicity into the car, to buy purchase certain items by simply using what is in the car, let's say, as display objects, where you could maybe transmit the sensation of textiles to the materials around you. So it's really get more of a, I would say, like a digital perspective of what's outside, but bring it into the car. So really make your third living space something that will really bring you, or let's say, give you the advantage of time. So and all this, let's say, infrastructure, so the cars will be really beginning to communicate with one another. So this is something that's already not state of the art. So it's there. So all this infrastructure and the way you interact, and so this would definitely be one of the prospects of the future. But digital food, not yet, but why not?
Why not? Let's do it. Right? No, it's fine. I mean, I think about this as a kind of augmented reality as well, right? Because I mean, when you are in the car, you can experience a lot of things, of course. I mean, in the surroundings, right? And to have the possibility to kind of get the augmented reality perspectives in the car, in the cockpit, could also be very interesting. And I think there is so much development here in this area that I think it's really, really inspiring and interesting, right?
Yeah,
I had
really
a question
exciting times.
Yes. So I had a question on the chat. Is Bosch being affected by the recent semiconductor shortage? In the long term, do you see electronic cars as a sustainable solution? So amount of electronic waste, because I mean, more and more sensors goes in the car, of course. Batteries is maybe the form factor will be the car in itself is the battery in a way, right? So do you see this as this electronic waste a big problem?
Good. So first question, yes, we are being affected. So as other,
shortage,
it's something that's global. So there is a certain, let's say, high demand for certain components that we are also using in our navigation and instrumentation system. So fortunately for us, we as Bosch have been able to mitigate, let's say, this quantity or less quantity, and we have not, let's say, as of yet, had any implication to any OEM. So that's going fine. With regards to EV vehicles as a sustainable future, for sure, I think that there is still some work to be done with regards to the life cycle analysis of these products. We know that, for instance, the combustion engine is something that's been around for years, and there's a lot of information regarding this, especially recyclability of materials. Definitely still some work to be done there. We know that ourselves, Bosch, so we are also pushing for the electrification of this, but we still are also, let's say, developing new fossil fuels, or not fossil fuels, but synthetic fuels, in order to, let's say, to fill in this gap, to bridge the gap. But to be honest and clear, I think still a lot of work has to be done to really understand the impact of these electric vehicles, especially these components, and how the waste will be generated and how the waste will be treated. So definitely a object for study for sure. Yes. So no really clear answer there.
Thank you so much. And thank you again for your presentation. Now it's time to conclude this session, and it's terribly late, so we have overdrawn more than 30 minutes. I'm very, very sorry for that, but I think the presentations were excellent and very, very interesting. So I hope you all can manage to take a little bit shorter lunch break and think it's worth the time to be with us today. And don't forget, now we have a new afternoon session coming up at starting 2 o'clock. And it will contain 2 sessions, one about materials as activators and promoters of prosperity and welfare. So very important. And then the last session for today, advanced materials towards a sustainable path. So I wish you all very welcome back after the break. So we should start again 2 o'clock CET time. So that is 1 o'clock here in Portugal for those of us that are in Portugal. Thank you so much, all of you. Okay. Thanks.
Thank you. Bye.